Now we're going to expand what we've done with hydrogen to deal with the electronic structure of atoms in general, and it turns out that this is a bit of a formidable task because although hydrogen is pretty darn simple, and the reason it's simple is because it only has one electron, and so the only forces involved in the atom are the attraction between the electron and the nucleus, and the physics or math to deal with this is sort of not too terrible, especially if you don't get into the quantum world if we use the simple approximation. But if we deal with multi-electron atoms, and or if we try to do things really taking into account the fundamental weirdness of electrons as having wave and particle aspects, it turns out that we hit some very formidable mathematics. This is the Schrödinger equation, named in honor of its discoverer, inventor, creator, however you want to put it, Erwin Schrödinger. He's one of a number of scientists who were instrumental in developing the field of quantum mechanics in the 1920s. And this is a partial differential equation that can only be solved exactly for hydrogen, but it can be used with approximations to get some reasonable results for other atoms. And now with the advent of powerful computers and programming, we can actually get pretty good approximations for even big complicated molecules. But this is quite outside the scope of our class. We're going to just simply look at some of the results of the theory, what we have as an understanding of electronic structure. And in this complicated equation, it turns out that this here, the Greek letter psi, represents something called the wave function. And the wave function, it turns out, describes what the electrons in the atom are doing, and in a sense it describes the location of the electrons in the atom. And more on that very soon as to the meaning of it. So essentially solving the Schrödinger equation gives us information as to what the electrons in an atom are doing, and we'll look at the results of this. So to do this, for the case of a multi-electron atom, like for example oxygen, one has to deal with the attraction of the nucleus to this electron, and to this electron, and to that one, and in fact to all of the electrons in the atom, but also with the repulsion of this electron and that one, and this electron and that one, and all of the inter-electron repulsions. And that's pretty complicated. So the electronic structure of the atoms other than hydrogen is complicated because each energy level or each energy shell, turns out it's split into sublevels or subshells, and then it turns out that each sublevel or subshell consists of several orbitals. And again, this is essentially what electrons and atoms do, and we have a description from it using some fairly complicated mathematics. So we're going to just kind of now cut to the chase of some of the meaning of these things. So here are the basics of our current understanding of electronic structure in atoms. First of all, an atom's electrons end up being grouped into different energy levels or different shells that surround the nucleus. These energy levels are described by the principal quantum number n, which can be equal to 1 or 2 or 3, etc. And we sometimes talk about the first energy level or shell, then the second energy level or shell, then the third one, but we'll see soon that they're not really circular orbits or really anything like that. They're much more complicated shapes. The energy levels that have a smaller n have lower energy, they can contain less electrons, and their electrons are on average closer to the nucleus. So electrons in the first energy level are lower energy and closer to the nucleus than electrons in the second energy level, which are in turn lower in energy and closer to the nucleus than those in the third, etc. Energy levels with higher or larger n have higher energy, contain more electrons, and are on average farther from the nucleus. Pretty much what we've already said. Now within a given energy level or a given shell, the electrons turn out to be grouped into subshells, which also have different energies from other subshells. These energy levels, these subshells, are described by the quantum number, which is called L, and it turns out L can equal 0 or 1 or 2 or anything up to 1 less than the principal quantum number. So if the principal quantum number is, let's say, 4, then L can equal 0, 1, 2, or 3, which is 1 less than 4. And L equals 0 corresponds to what's called an S subshell. L equals 1 corresponds to a P subshell. L equals 2 corresponds to a D subshell. L equals 3 corresponds to an F subshell. And that's as far as we will ever go. Now, the first shell only contains S subshell. The second shell contains S and P subshells. Third shell contains S, P, and D subshells. Fourth shell contains S, P, D, and F subshells, etc. And so here's kind of a way to show that as a bit of a grouping. And then within each subshell, electrons are grouped into orbitals, and all the orbitals within a given subshell are of the same energy. And it turns out that an S subshell has only one orbital, P subshell has 3 orbitals, a D subshell has 5, an F subshell has 7, etc. And so that is shown here, the shell number, the subshell designation, and the number of orbitals. And this is sounding like it's getting pretty complicated, but in just a moment we'll kind of see a general meaning of it. And one thing is that what's an orbital? Well, it's a region in space where specific electrons are most likely to be found. And each orbital has a different shape or orientation. So the s orbitals are spherical, and we'll find the electron somewhere within this region, more likely a little closer to the center, less likely as you get out to the edges. P orbitals are kind of dumbbell shaped, and there's 3 of them along the, we could say, x, y, and z axes. And so the electron's likely to be here, or in this p orbital, the electron's likely to be in this lobe of the dumbbell or that lobe, etc. And then the D subshells are more complicated looking. We'll maybe look at those in a bit. Now, the key thing is that the electrons fill into shells, subshells, and orbitals that are arranged, if you will, in the following way. Here's here's the first shell, second shell, third shell, and fourth shell. So that just shows the energy levels. And then as to subshells, there's only the S subshell in the first shell, so 1s is the only possible subshell. But in the second energy level, you can have S and P subshells, and the S subshell is lower in energy than the P. The third energy level, has S, P, and D subshells, with S lowest in energy, P higher than that, and D higher than that. And then the fourth energy level, we're going to run out of room, has an S subshell, a P subshell, a D subshell, and also an F subshell, which are going to go off of our graph here. And then, finally, within the subshells are orbitals, and the 1s subshell only has the 1s orbital, the 2s subshell only has the 2s orbital, but the 2p subshell has 3 different 2p orbitals. Back to the 3s, only 1, 3p has 3 orbitals, 4s has 1, 3d has 5 different orbitals that are all called 3d, 4p has 3, and then again they keep going, and we're going to run out of space. And the way to look at this, and we'll do some examples in the next screencast, is that these orbitals are kind of like an electron hotel, and these are the places where electrons can live. So they can live in the 1s room, or the 2s room, or the 2p room, well, actually one of several 2p rooms, etc. And we'll see that electrons have rules for what they like to do. They like to be at lower energy, they like to be in separate rooms if possible, and more. Now, this is essentially like saying that the electrons in an atom live in an electron hotel, where the first floor of the electron hotel, the lowest energy part of the electron hotel, is the 1s orbital, which is kind of like a room where electrons could live. There's a 2s orbital and 3 2p orbitals in the second floor, if you will, of this electron hotel. Then 3s, 3p, and 3d, each of which are slightly higher than the previous subshell in terms of energy. Then 4s, 4p, and 4d, and the 4s orbital is a little lower in energy than the 3d orbitals, and it keeps on going, as shown here, and again kind of went off scale eventually. Now, electrons and atoms are found in these subshells, in these shells, in these orbitals, according to some rules where the energy levels or shells are characterized by the quantum number n, which is either 1 or 2 or 3 or 4 or 5, etc. And so those correspond to the energy levels or shells, the first shell, the second shell, the third shell, the fourth shell. The sublevels or subshells are characterized by letters S, P, D, and F, and in terms of quantum numbers, which we'll see soon, S corresponds to an L quantum number of 0, P corresponds to an L quantum number of 1, D is L equals 2, F is L equals 3, etc. And then the orbitals are the rooms within the subshell. The S only has one possible orbital, but P has 3 possible orbitals, sometimes characterized as P sub x, P sub y, and P sub z, like the x, y, and z axes. D has 5 orbitals, F has 7 orbitals, etc. And then it's also worth noting that the electrons have a quality called spin, in which case they behave as if they were little spinning charged particles, and spinning or moving charge behaves as if it's a little magnet. And so spin is kind of like having a magnet that has a north pole that can either point upward or downward. And so we often designate an individual electron by an arrow, and either it points upward, indicating it has a spin up, or it points downward, indicating it has a spin down. And then we'll place these in the rooms in the electron hotel according to the rules the electrons follow in terms of how they are organized in the electron hotel. So an atom's electron configuration describes the specific arrangement of the electrons within the atom and within the subshell, the shells and subshells. And we can use the rules that are about to follow, the structure of the periodic table, and put those together to predict what's called a ground state, which is the lowest energy electron configuration for an atom. And one way to remember the ordering is, as we start in the upper left corner of the periodic table, we go from the 1s orbital, then to the 2s, and then the 2p orbital, then to the 3s, then the 3p orbitals, then 4s, then 3d, then 4p, then 5s, 4d, 5p, then 6s, down into the lanthanides for 4f, then 5d, then 6p, and finally 7s, 5f, 6d, and that gets us through all of the naturally occurring elements. Now here are the rules that electrons follow in atoms. Electrons occupy the lowest energy orbitals that are available, so we could kind of anthropomorphize electrons and essentially say they're lazy. They like to be at the lowest energy state possible. Second, an orbital can hold at most 2 electrons, and if it has 2 electrons, they must be of opposite spin. So again, anthropomorphizing, that's sort of like saying that a room in the electron hotel can have at most 2 electrons living in it, and they must be sleeping in the room, let's say, oriented differently, head to toe and toe to head. When we have several orbitals at the same energy, then each orbital only gets 1 electron, all of them having the same spin, until all of the equal energy orbitals are half filled. And one more anthropomorphization is that if electrons have a choice of rooms all on the same level, they'd prefer to have a room to themselves rather than share a room if they don't have to climb any stairs or spend any more energy to do so. So this is usually most easily seen by example. We'll start with the simplest example and work through a few slightly increasing in difficulty. So let's start with the element hydrogen, which only has one electron. Hydrogen's electron wants to be in the 1s orbital, and it's going to have a spin, in this case shown as up. So we draw an arrow pointing up in the 1s orbital, and then for hydrogen we can represent it by H, and we would say its electron configuration is 1s1, where the first one represents the energy level, the first energy level. The S represents the S subshell, and there's only one s orbital. And then the superscript 1 indicates that there's one electron in the 1s subshell. Helium is the second element, 2 electrons, and the second electron for helium also wants to be at the lowest energy possible. There's room in the 1s orbital or 1s room for that electron to go into, but it has to have the opposite orientation or spin. And so we now have 2 electrons in the 1s orbital or 1s subshell, so we say the electron configuration for helium is 1s2, where the 2 superscript indicates 2 electrons in the 1s subshell. If we do the element lithium, which has 3 electrons, first 2 go in the 1s subshell, and the third electron goes to the next lowest energy level, which is 2s, and we will now have 1 electron in the 2s subshell or 2s orbital. So we would say the electron configuration of lithium is 1s2, so 2 electrons in the 1s subshell, 2s1, which means 1 electron in the 2s subshell. Nitrogen. Now we're finally jumping more than one element ahead at a time. So here is nitrogen, and it has 1, 2, 3, 4, 5, 6, 7 electrons. Its atomic number is 7. And so the electrons will fill in with 2 in the first shell, in the 1s subshell, then 2 electrons in the 2s subshell, because this one had more room, so now we have 4 electrons, and we're 1s2, 2s2, and now the 5th, 6th, and 7th electrons are going to go into the 2p subshell, but they will be in separate rooms, but all having the same spin direction. So 1 electron in this 2p orbital, 1 electron in this 2p orbital, and 1 in this one. And since we're now dealing with the 2p subshell, we will say 2p3, indicating within the 2p subshell there are 3 electrons. Jumping a little further ahead, now we'll do fluorine, which has 9 electrons. And now we're not going to draw boxes, we'll just draw lines. And so 1, 2, 3, 4, 5, 6, 7 electrons gets us up to what nitrogen had. And now we need 2 more electrons to get to fluorine, and they will go into the lowest energy subshell, which is the 2p. But now, since each of these orbitals has 1 electron in it, the 8th and 9th electrons will go into existing orbitals that have 1 electron in them, but with opposite spin, and they will therefore pair and fill up those rooms. And so now we have 1s2, 2s2, 2p, 1, 2, 3, 4, 5 for the electron configuration for fluorine. Now a couple things to note. The 1s2 corresponds to totally filling the first shell. So we call these inner shell electrons because here we have electrons in the first shell and in the second shell, and the first shell is inner while the second shell is outer. So we have 7 electrons total in the outer shell, and outer shell electrons are also called valence electrons. So we could say for fluorine that its valence electrons are the 2s2, 2p5 electrons. Or we could say there's a total of 2 plus 5 or 7 valence electrons for fluorine. The inner electrons are also sometimes called core electrons, so we have 2 inner shell or core electrons for fluorine. How about silicon? Well, if we count up the number of electrons in silicon and put them in the appropriate place, what we end up finding is we fill the 1s subshell, then the 2s subshell, then the 2p subshell, next comes the 3s subshell, and then finally we have a couple electrons going into the 3p subshell, each in separate rooms, and we have a total of 14 electrons for silicon, 2 in the first shell, 2 plus 6 or 8 in the second shell, and then 2 plus 2 or 4 in the third shell, and we would write this as 1s2, 2s2, 2p6, 3s2, 3p2. And the inner shell electrons for silicon would be the first and second shells. So 1s2, 2s2, 2p6 for a total of 2 plus 2 plus 6 or 10 inner shell or core electrons. And then the valence electrons or outer shell electrons are the 3s and the 3p, so 2 plus 2 or 4 outer shell or valence electrons for silicon. Note that this is what's called a ground state or lowest energy electron configuration. An atom of silicon could have a different electron configuration where an electron, let's say one of the 2p electrons, absorbed energy from some outside source and was bumped up to a higher energy level, like maybe the 3p or the 4s or something higher, and it would have the same total number of electrons, but it might be 1s2, 2s2, 2p5, 3s2, 3p3. So one less in the 2p and one more in the 3p. That would be immediately recognizable as a not ground state electron configuration because that's not the lowest energy electron configuration that silicon could have. Again, it's worth noting that the periodic table is a good guide to the ordering of filling the subshells. Start at hydrogen. 1s is the first row, 2s, 2p is the second row, 3s and 3p is the third row, then 4s followed by 3d followed by 4p is the fourth row of the periodic table, and notice that the third subshell or third shell are starting to kind of overlap each other. And then 5s, 4d, 5p, 6s, 4f, 5d, 6p, and then 7s, 5f, 6d, in that order, fills out the rest of the periodic table, and we can think of these as being the s block electrons. So this will be the highest energy electron in an s block. Here are the p block electrons. Highest energy electron will be in a p subshell. D block electrons and F block electrons respectively.